All right, recording is rolling. It is Friday, January 19th. We're going to take today to solve these Doppler puzzles. You guys got this Doppler page in front of you. Let's see, for recording context, I did print this on the opposite side of the Speed of Sound Lab. All right, get back to you guys. Oh, a bunch of guys just turned in your chapter 1450 puzzles. Thanks for doing that. Get those in the grade book. And you guys' harmonic motion waves quiz, you guys remember that is due on Mondays. Got a few days there. All right, so Doppler puzzles. Let's take a look. Doppler puzzles. All right, so I have here, show you guys the organization of this. I got 4 different scenarios. Here's scenario 1, scenario 2, scenario 3, scenario 4. You guys remember? I think it was last week. I had the Doppler ball. I was swinging that around a circle. Hear the frequency going up and down, right? Or I think you were. I was at the center of the circle, so I couldn't hear the Doppler shift, but I think you guys did. So if you're out by the sidewalk and a car goes by, you perceive a pitch shift, right? So that's this right here. Here is show you guys the organization of this. Right? Here is the source frequency. Here's the observed frequency. Right? So if this car is blaring its horn at some frequency, on your printed page, I gave you how many hertz that is. So beep, beep, there's some frequency associated with that. I also gave you guys the speed of the car. The first scenario, I got 2 observers. One observer, the car's headed towards, one, the car's going away from. Right? I help you guys out a little bit here. Guys, person A, the car's going away from. Person B, the car's sort of headed towards. Which guy here perceives a higher frequency? A or B? B. Here's a higher frequency, right? So part of the fun today is figure out how do you navigate this plus or minus here to achieve that effect, right? Like here, start real basic. What if the car was parked? If the car is parked, then isn't it true everybody perceives the same frequency, right? Right, and that would just be this. The observed frequency is equal to source frequency, boom, end of story, right? But if you put somebody in motion, either the source, which is the car, or the observer, which is this little stick figure guy, right? Or both, right? Now this whole fraction opens up. Here's speed of sound, which I gave you guys speed of sound. Let's call it 343 meters per second today. Right? That's pretty good, right? And then here's plus or minus the velocity of observer, plus or minus velocity of source, right? So how can you apply, say, a plus or minus to which one to achieve either a higher or lower frequency? Right? Here's the way we do this is I'm going to give you guys 20 minutes to work with your teammates, see if you can solve all 4 scenarios, and then about the last 10 minutes of class, I'll come in and debrief this with you guys real fast. If you feel good about your answers by the end of class, you can turn in the grade tray. If you think you have to go fix some things, then you can turn it in Monday. All right, there's the clock running. All right, so go ahead. All right, recording is resumed. If you're watching the video, we just hit time jump for 20 minutes in the future. Let's go over the answers. All right, so scenario 1. So I told you the speed of the car. I'm going to write this 25 meters per second. Show a little bit better on the camera. And I gave you guys a frequency of so many hertz. Mine says 440 hertz. Just usual, I have a bunch of different versions of this. I think I gave us all the same speed of sound, though. The speed of sound, I'm calling 343 meters per second. Right? And so if you're inside the car, what frequency do you hear? Guys, if you're along for the ride with the car, do you hear anything different from if the car was parked? No. Oh, right. So could you guys just copy paste that car horn frequency that I gave you? Yeah. Right? Which your answer is not 440. Your answer is whatever I gave you, right? But mine says 440 hertz, right? Yeah, also, all these numbers have units on them, right? I've been here. Watch you guys homework puzzles. A lot of you guys remember numbers have units attached to them, but some of you guys are a little fuzzy on that. So 440 hertz, right? Or guys, if you want to overcomplicate this, suppose the car was going at so many meters per second. I gave you car speed too. Mine's going 25 meters per second. Let's go to highway speed there, right? Could I go? Say the observer and the source are moving along together. So you're going to do speed of sound minus 25 over speed of sound minus 25. I would still have a ratio that's equal to 1. This whole ratio would still be equal to 1, even if I overcomplicate it and plug in all these numbers, right? And so the observed speed is still the source speed. Sorry, observed frequency is still the source frequency. Still a match. Right, you guys good on that? Okay. All right, now person A and person B. All right, we're going to do real basic Doppler setup here. So I'm going to go the observed frequency is equal to the source frequency, which for me is 440 hertz, multiplied by ratio. Right? Let's do it for person A, and then later on I'll do observed frequency for person B. Okay, they're going to start out the same way, 440 hertz times the sum ratio. Okay. So they get speed of sound. Speed of sound. Okay. Yeah, so I gave everybody speed of sound is 343 meters per second. Okay. No, these two guys, it says they're just standing there at rest. They're stationary. That's what it says. They're stationary. So isn't it true if they're stationary, the speed of the observer would be what number? 0. So you can say like plus or minus 0, or plus or minus 0. Right, so whatever there. Right. But the car, right? Now here's the first application of Doppler effect. You gotta apply some critical thinking here. Okay? Let's start with person A. Guys, this car's going away from person A. Is that going to result in person A hearing a high or a low frequency? A low frequency. And how are we going to get there mathematically? Like, what's the Earth? Wait a minute. If you subtract on the bottom, it makes the denominator small, which makes the overall fraction what? Big, like bigger than 1, which will give you a high frequency. Wait, isn't it the opposite what you want? So you have to do what down here? Yeah, add the speed of the car. So for me, that'd be 25 meters per second. Okay, and then for person B, could you just switch this to minus 25 meters per second? Okay, you guys have something like that. Okay. What you should get is that person B hears a higher frequency than person A. Okay. I'll run my numbers while you guys are checking your own math. Okay. Then, okay, so I'm getting my person A is hearing 410 hertz. And my person B, scroll up, scroll over, replace point about 475 hertz. Okay, so boom versus boom. Okay, go ahead and write this in here. Of course, your numbers are different than my numbers, but you should see person A should hear a lower frequency than the car horn at rest, right? And person B should hear a higher frequency than the car horn at rest, right? Okay, is that right? Okay. Scenario 2 is identical to scenario 1 with one change, which is that person B is now running towards the car. Guys, if person B is running towards the car, what's going to happen to the observed frequency just due to running towards the car? It's going to go up, right? Right. So I see in this formula as something with this right here, right? Like the speed of the observer. Should I say plus or minus up here? Running towards the car. How about plus? Yeah, because that's going to pump up this fraction larger. There's just that effect in isolation. Okay? So let's do frequency observed for person B and scenario 2. It's equal to, let's take 440 hertz times, all right, do 343, okay, plus, how fast did I get going? 5 meters per second. Although same bolt going on right there. 343 meters per second. Still minus the 25 meters per second. Okay. Okay. So we got two effects going on. The car is headed towards the person, and the person is headed towards the car. And both of those are causing the observed frequency to go up. Right? That'd be true, right? Let's try this out. It's 440, 343 plus 5, and parentheses over 343 minus 25. Right. Make sure you got order of operations and everything grouped correctly, blah, 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 blah. Right. I'm getting about 482-ish hertz. I'll call it 42. 32 hertz. Right. Now, if you did everything correctly, then at this point, this should be the highest frequency so far. Notice by running towards the car, it increases the frequency above standing still. Right? Like if you compare these two. Right? Right? Yeah, there it is right there. Right? Okay. Some textbooks emphasize the fact that if these are going in opposite directions, the car's headed to the right and the guy's running towards the left, that you have opposite signs in the Doppler equation, right? And if they were the same sign, that might indicate that they were going in the same direction. Right? I like to work at logically if like what should increase or decrease the frequency, right? But some textbooks do it the other point of view. Right. Scenario 3. Now this car is rolling down a hill. I gave you the height of the hill, and I gave you the gravity field is 9.8 meters per second squared. And Also, for funsies, I got person D running away from the scenario. He's trying to run away. So now this is going to be like a multi-part. First, you got to figure out what is the speed of the car at the bottom of the hill. How do you figure out the speed of the car at the bottom of the hill? You guys remember this from last semester? Sum of energy initial equals sum of energy final. Guys, what kind of energy at the top of the hill? You're on, right? So potential energy mgh at the top. Kinetic energy 1/2 mv squared at the bottom. Okay. We're solving for what is the speed of the car at the bottom. Solve for that. Oh, I never gave you the mass of the car. Oops. Wait, no. Goes away anyway. Okay. Solve for v times 2 square root. The speed of the car is square root 2gh. Yeah, you guys remember Galileo dropping balls off Leaning Tower back in 1589? I was there. You guys remember that? And this was how fast that they were crash landing to the ground. Square root 2gh. So let's figure out. The speed of the car at the bottom of the hill is 9.8 meter per second squared. And then whatever the height of the hill is. My hill is 15 meters tall. Right, make sure it's all square rooted. Right. Now you got the speed of the car. Right. Now we can flip over to the frequency observed by person D is the source frequency, which is the same car horn's been blaring all along. Right. Now that's my car horn. You guys have a different car horn. Okay. We're gonna multiply by ratio. I got speed of sound is still here, speed of sound. Okay. Right. Oh, guys, running away from the car, should I add or subtract on top? Subtract. And he's running this fast. I'm trying to get away. And then the car going towards him, should it be adding or subtracting on the bottom? Also subtract. Right? Because that would decrease the denominator. It's going to blow up the fraction bigger. He's going to perceive a higher frequency due to the car rolling toward him. Yeah. Right. And then I'm going to take, that's what I did all the square root 2gh stuff for. That's going to, I'll call speed car, whatever number that is. Right there. Right? That's it. Also, notice minus on top, minus on bottom. The fact that both signs are the same, in this case minus minus, is an indication that both objects are in the same direction. Yeah, they are. The car is rolling towards the right. This guy's trying to run away towards the right. Right? Minus minus. Right, all good? Right, finally, scenario 4. Now we equip this car with rocket boosters. It's going 600 meters per second away from E and towards G. Okay? So if you're inside the car, suppose there's a bubble of air inside the car, is traveling along with the car. Do you think you perceive the same frequency as the car horn at rest? Yeah, right. All right. So let's say that. Just go ahead. Right now, person E. Should I, for person E, say frequency perceived by E is the frequency of the car horn times speed of sound? Right, speed of sound. Right. Well, person E is at rest, so plus 0 on top. Right. Now, guys, going away from person E, should you say plus or minus on bottom? Plus. Plus. And then speed of car. Right. Now that's for person E. Now for person G, who the car is headed towards. Oh, yeah. Did you guys reach for a minus down here? Towards, right? How many of you guys ran the equation for person G and got a negative number? Right? Now, can you have a negative frequency? Does that make sense? I'm going to think this is a trick question. Right. How many of you guys figured out what's going on there? What's my Griffin trick? Tricky Griffin. What'd I do? What is the action here? Oh, you guys hear Josiah? Nailed it. Josiah figured out it's a supersonic car. You guys notice 600 meters per second is greater than 343 meters per second? This car is, guys, if person G standing over here, what's going faster? The car or the sound waves from the car? The car's going faster. What's going to reach this guy first? The car. Does this guy even hear the car coming? No, because the sound waves don't reach him. Right? And until they do, then they reach him all at once, right? And then does this cone wave? He perceives that as a what? SB. Sonic boom. Sonic boom. Right? He'll hear the car after it passes. Right? Now he's in person issues. Right? Yeah, he never even hears the car coming. Never even hears it coming. So I would just say no sound. Right? Right. If you think you got all the right answers, turn that to gray tray. If you think you need to fix a few things, then you can turn that in on Monday with your quiz. All right, and that is a wrap on the week.